This institute will greatly enhance the research in this area, as well as the commercialization and uptake of those opportunities. I'm thrilled to have introduced Professor Hinton today, our Nobel laureate, Professor John Polanyi. John is a university professor in the Department of Chemistry. I won't try to read all of his awards and honors that I have listed here, because that would take up all of Professor Hinton's time. But I will note that he's been recognized for his brilliant scholarship in fundamental science, the Nobel Prize, as well as many other honors. But I also want to note that he has been a wonderful citizen of the university, of the country, and of the globe, and has spoken eloquently and passionately about a range of topics, including science funding, disarmament, and peacekeeping. And it demonstrates all the great values that we expect in our faculty. Thank you, John.
This rock festival atmosphere is a fantastic testimonial to interest in entrepreneurship, and also to my colleague in chemistry, Cynthia Go, who founded the Impact Center, which has spawned many relatives which have booths around us here. And I also want to doff my hat in the direction of our revered President Research, Vivek Goel, who you just heard speak. Today's announced speaker, and surely part of the reason for this vast audience, is Professor Geoffrey Hinton, and he is the embodiment of the Impact Center's mission. He's poised near the pinnacles of both basic and applied science. And I want to add that these pinnacles, these mountain tops, belong to different mountains. Mount Discovery at the basic end, Mount Innovation at the applied end, which many of you are involved with. And as you just heard, with the establishment in Toronto of the Vector Institute, which was announced last week, a few days ago, the two peaks, the two mountain peaks I just referred to, will become geographically much closer. And that's a highly welcome development. The peak that is linked most closely to the University of Toronto, on whose campus we meet today, gives primacy to discovery. And that's vital to things like the Impact Center, since you can't for long apply what you don't understand. Happily, the new Vector Institute for Artificial Intelligence has as its chief scientific advisor Geoffrey Hinton, to whom I shall yield the stage in just a moment. And it also has as its director of research, a very important position, Dr. Richard Zemmel, who, like Geoffrey Hinton, is a renowned academic. And both, of course, are ornaments of the field of artificial intelligence. There's nothing artificial, however, about their intelligence. Geoffrey Hinton comes with links to Cambridge University, Carnegie Mellon University, the University of Toronto, and the Canadian Institute for Advanced Research, as well as being recipient of Canada's highest scientific accolade, NSERC's Hertzberg Prize. His research, as you know, deals with a very fundamental question, fundamental to all of us human beings gathered here. How does the brain work? How do we translate electrical impulses into images we can recognize? And that question was posed to Geoffrey Hinton, our speaker, by his PhD supervisor. Quite a few of you have PhD supervisors, and that particular PhD supervisor was also a supervisor of my own PhD work with absolutely no results. The fateful meeting between that supervisor, Christopher Longwood Higgins, and our speaker, Geoffrey Hinton, took place at Edinburgh University, and Geoffrey took the hint and turned the light of his intellect inward onto his own mind. Mathematics, he found, had a lot to say about turning electricity into meaning. And as you're going to hear from this, he identified a subtle backward progress in which the more developed expert knowledge illuminated the prior less expert. And I mention this because it's a charming insight. It'll doubtless come to the fore in a moment. And also it suggests a parallel with the functioning of a university. You pretty much, most of you belong to a university, most of you to this university. At universities, teachers attempt desperately to explain things to their students. And in the course of trying to explain things, they improve their own understanding. And so it's this to and fro process between teacher and student, this refinement of knowledge through toing and froing that binds together our academic community. Now, today's event, I shouldn't close without mentioning, celebrates not just knowledge, which I've been stressing, but also the marketplace into which knowledge is passed. Markets are also engaged in searching for understanding, and it's a very tough road which many of you are taking. What they want to understand, the markets, is something different from what the university wants to understand. The market wants to understand utility. Well, naturally, the marketplace tried to lure Geoffrey Hinton away from the University of Toronto. Sensibly, they didn't try very hard. So here he is, before you, somewhere, hidden away, back at the institution to which he has contributed so much. I just add a paragraph suggested to me by Vivek Goel. This event marks Geoffrey as, and you just heard it, a Royal Bank lecturer. We owe a lot to the Royal Bank here. He is, in fact, a scientific royal. On his website, if you take a look, you can see displayed his intellectual antecedents extending back. That is royalty as it should be. So I give you our royal lecturer, Professor Geoffrey Hinton.
Thank you. So I would like to thank RBC and the University of Toronto for organising this event. It's true, as John Polanyi said, that mathematics is very important for neural nets. And I'm actually very good at explaining the mathematics because I'm no good at mathematics. And so I'm able to explain it to other people. Can we get the lights down on this? There's two ways to get there used to be one way to get a computer to do what you want. And that was to write a program. And that meant figuring out how you would do it yourself and then explaining it to the computer in excruciating detail. Now there's a new way to get computers to do what you want. First you write a program that tells the computer how to pretend to be a network of neurons with a learning algorithm in it. And then to do any particular task, you just show it examples. You show it examples of what goes in and what you would like to come out. So for example, for this task, you would like to look at an image and produce a caption for the image. Now, people in AI tried to do that for 50 years, and they didn't even get close. They couldn't even recognize the objects in the image. We can now train a neural net that starts off knowing nothing, and you show it the pixels in this image, and it will output this caption. In fact, this is an example that the neural net had never seen before. It saw this after it was trained, and that's the caption it output. So how does that work? Well, I can explain what a neural net is. I'm not just going to show you examples of the wonderful things they can do. So first of all, we need to make an idealization of a neuron. It's a very gross idealization, but it's good enough for what we need to do. We say a neuron gets some inputs from other neurons and occasionally from the senses, and it gives an output that depends on how big the inputs are and how big the weights are in its connections. So what it actually does is on each input line, it multiplies the input by the weight, adds it all up. If it gets a big sum, it gives a big output, like the graph on the right. If it gets a small sum, it doesn't give any output. That's it. That's how a neuron works. One of our idealized neurons. Real neurons are much more complicated. Then we have to figure out how to put them together to do a computation. So we put them together in layers like this. We have neurons at the bottom that represent things like the intensities of pixels. We have neurons higher up that are going to learn to be feature detectors. But we're not going to have to define the features. It's going to learn the features. And then neurons at the top that make decisions. And to train the system, we can either use supervised learning or unsupervised learning. In supervised learning, you tell it the right answer. That's what works best at present. It's not really what people do. People mainly do unsupervised learning, where you just look at the data and figure out what's going on. That's much trickier, and we're working on that, but we haven't made that work very well yet. So I'm going to give you an idea of how supervised learning works. You put in some data at the bottom, for example, a picture of a cat. And let's suppose we want a neural network that can tell the difference between a cat and a dog. So it has two output units, one that says cat and one that says dog. And this neural network at present is giving a bigger output for dog than for cat. So that's not very good. So here's an algorithm that will work, but will be very slow. You pick one of the weights in the network, that one shown in red, and you look at the output with that weight, and then you change the weight. So we make the weight a bit bigger, and we notice the output changed a bit. In fact, it got more cat-like and less dog-like. So that's good, because this is a cat. So we'll keep that change that we made. And then we'll go and find another weight, like that one. And we'll try changing that weight, maybe making it a bit stronger. And we were lucky. So again, cat went up and dog went down, so we keep that change. And we could go around all of the million weights in the network, making a change and seeing if it helps, and keeping it if it helps, just like in evolution. And so we go around all a million weights, or maybe a billion if you've got a big network, just for that one image. And then we come to the next image, and we do it all again. And so having gone through millions of images and billions of weights, it would have taken tens of thousands of years, but this algorithm would clearly work. But it would work in evolutionary time. So we can actually do the same thing by just using a little bit of simple mathematics. And we can make it much more efficient. So what we do is instead of perturbing the weights one at a time and seeing whether it helps, we look at the output we're currently getting, we compare it with the correct output, and we send a signal backwards through the net that's computing for every single weight in the net, what direction to change it in so as to make the output more like what we want. And the difference between these two algorithms is simply that if you've got 1 billion weights, the second algorithm will be 1 billion times faster. Okay. Now for a computer theorist, that doesn't really mean much because 1 billion is not much. It's not like it's exponential. But for practical computer people, it's important. So we send that signal backwards through the network. I'm not going to go into the math. If you're a mathematician, it's just the chain rule for computing derivatives. And then you update all the weights, and then you take another example, you update all the weights, and if you keep doing that long enough, it gets to be very good. So this algorithm, many different people realized this algorithm in the 70s and 80s. In the mid-1980s, computers were fast enough so that we could show that if you ran this algorithm in a multi-layer net, it would learn good representations. That is, the features in the middle layers would discover meaningful things about the data, even though you hadn't told it what features to use. And that was exciting, because that was a central problem in artificial intelligence. Where do representations come from? And in these networks, the representations are activities of a whole bunch of feature detectors, a vector of activities, and so they use vector representations. In classic AI, representations are symbolic expressions operated on by rules of inference. Here we just have vectors operated on by matrices, and that turns out to work much better. It was used for reading numerical amounts on checks, or detecting credit card fraud, or interpreting pap smears, but it never worked really well. And in particular for deep nets, with many layers of feature detectors, it didn't work as well as we hoped. So by the 1990s, psychologists were still very interested in it, but people in machine learning have pretty much given up on it because they had other algorithms that were simpler and more reliable and worked just as well, if not slightly better. And then, at the beginning of this century, well, earlier on this century, researchers in Canada came up with new techniques that enabled these nets to be trained faster. I'd love to go into all those new techniques, because that's what I really care about, but that's not the main point. That's sort of going into the dust of history now. The main point is that this algorithm, with big data sets and fast computers, works really well. So the first big breakthrough that had sort of major industrial consequences was for speech recognition. Two students at the University of Toronto made a net with a bunch of these hidden layers, and they trained it. It would look at some frames of coefficients extracted from a speech wave, and it would try and predict which piece of which phoneme the person was trying to say in the middle frame. And it did better than previous technology, only slightly better. But the point is, this was two students over a summer, and they'd beaten 30 years of intense competition by big groups. And so it was obvious to everybody that this was going to win. And other students went off to various places. One of those students, Navdeep Jaitley, went to Google, and Google said, no, we don't want you to work on this. It's not going to work. And he insisted, and they were amazed it worked. They were very good. They let him do it, and it worked. And as soon as they saw that it really worked, they put a lot of engineering into it. And by 2012, it was out in the Android. That was the first big deployment of this new technology. And now all of the best speech recognition systems use some form of this. In 2012, two other students in Toronto showed that this stuff works very well for recognizing objects and images. There was a public competition where the best computer vision groups in the world entered their entries, and the test data was hidden, so you couldn't cheat. And at the bottom there, you get the world's leading computer vision groups, and they were getting about 25% errors. And we got just under 16% errors, almost half the error rate, and that had a huge impact on computer vision. Within a year, all the computer vision researchers had switched. Up until then, they'd all been saying, these neural networks, they're crazy. There's no way you're going to learn everything in all these layers just from data. You have to wire in sensible knowledge about vision. When this happened, they said, they were very impressive actually, they said, oh, we were wrong. And they started on the method that worked. That's very rare in science. What's interesting is over the next 3 years, the method got a whole lot better, because lots of groups are now working on it. It's now down to about 5% on this same data set, which is about human performance level. If you look at what the data looks like, I don't know if you can see this, that's a close-up of a cheetah, and at the bottom of the network's guesses, with how confident it is, it's very confident that's a cheetah, but its other guesses are pretty sensible guesses. If you look at this, it thinks that's a bullet train, even though, for example, the building in the background is much bigger, and there's a passenger on the platform, but it thinks it's a bullet train, and the other guesses are reasonable. Here, it gets it wrong. Its first guess is scissors, and if you look at its third guess, frying pan, you look at that and you can see this neural net needs glasses, right? You can see why it thinks it's a frying pan, but it's not really seeing too well. But the good news is, its error is a sensible visual error. It clearly sees what things look like. A few years later, essentially the same method was used to solve a major problem in game playing, which is, when you play chess, you can just get a computer to consider the moves, and then consider what the opponent might do, then consider what you might do, and search for a depth of like 12, and you can beat any person that way now. Go, you can't do that, because there's too many moves, and you need intuition. You need an intuitive sense of which moves are worth considering. You also need to be able to look at a board and say, is that good for me? And AlphaGo had 2 neural nets. That's how it differed from previous systems playing Go. One could look at a board and say, these are the plausible places you might move. It didn't always agree with the experts. There's the famous move 37, where the experts couldn't even put the stone in the right place on the board because it was such a bad move. It won the game, though. And another neural net that looked at a board and just said, how good is this for me? And those extra ingredients made a system that could beat the world champion at Go. In fact, I think it's only ever been beaten once by Lee Sedol in Game 4. Since then, it's played 60 games against experts and just won them all. Another example is some work done at Google that was published recently on looking at images of the retina and predicting what stage of diabetic retinopathy this is. And this network is now as good as most doctors. The very best doctors are still slightly better than the network, but not for long. And this is going to be very important, because, for example, a lot of people in India have this disease, and there aren't enough ophthalmologists to look at all these images. You can get the images, but you don't have the trained people to interpret them. But this can now, soon this will be done on a cell phone. This will be amazing. And for all of you, pretty soon on a cell phone, in the next year or two, I predict, there'll be a system where you can show a patch of your skin to this system, and it'll tell you if that's a cancer or not. And the problem for us is, you get this funny patch of skin, and you know it's not a cancer, but you're not quite sure. And you don't want to go to the doctor, because the doctor sort of laughs at you, of course that's not a cancer. It's much better to have a cell phone, because it won't laugh at you. Okay. I'm now going to talk about another kind of neural net, a recurrent neural net, which is probably where the most excitement is now. These were developed in 1997, or the modern algorithm was developed by a Hochreiter and Schmidhuber, who wrote such a bad paper about this wonderful idea that nobody could understand what they were talking about, and people just ignored it. And then in 2007, Alex Graves, one of Schmidhuber's students, showed that it really worked well, and since then it's been taking off. So I'm going to be very brief about a recurrent neural network, and I'm going to suppress most of the details. The networks I gave you before had layers, and this has layers, but these are layers in time. So in a recurrent neural network, you have some input neurons. I only drew one. The input neurons provide input at each time step to the hidden neurons. The hidden neurons are then a recurrent system. So at time step 2, the input to a neuron comes from the hidden neurons at the previous time step, plus the current input at time 2. And at any time, these neural networks can give outputs. And you train them with the same training algorithm. Basically, after a while, you know what output you want, and you send information backwards if the output's wrong, saying, please change the weights on these connections so I'm more likely to get the right output. So, working with 2 students, Ilya Sutskeva and Alex Krzyzewski, sorry, James Martins, In about 2011, we fed 500 million characters of Wikipedia to one of these nets. So the net starts off knowing nothing, and its job is just to predict the next character in Wikipedia. And that allows you to answer the philosophical question, which is, suppose you had an intelligent system, or even a dumb system like this, that just saw the character stream of Wikipedia. It didn't see the world, and it didn't get to talk to any linguists or philosophers. It just saw the character stream of Wikipedia. Could it understand the meaning of life? And most philosophers will tell you that's not possible, but I can give you some empirical data. So we trained it up, and it's just trying to predict the next character. And it predicts a probability distribution. It says, there's 86 characters I know about. Having seen these characters, I think the probability of a space is 0.9, and the probability of a Z is 1 in a billion, and so on. It has 86 probabilities that add to 1. If you want to see what it believes, you feed it a string of characters, ask it what it thinks comes next, it gives you some probabilities. You pick one of those according to those probabilities. So if space was 0.9, 0.9 of the time you pick space. And you say, okay, the next character actually was a space. What do you think comes next? And it'll give you a prediction. And so you can keep running this prediction game and picking from the bets it makes to see what you end up with. So we gave it that. Now, if it had said 42, that would have been boring, because that's in Wikipedia for sure. But it produced a long character string, and only small parts of this character string in Wikipedia. It just made something up. And you can see what its prejudices are from what it made up. And remember, it was trained on stuff on the web. So it's going to print out one character at a time until it reaches a full stop. And this is what it said. Now it's slightly confused, but I would argue that it's almost got the meaning of life just from reading Wikipedia. Now, actually that wasn't the first thing it said. We let it do it 10 times, and it may surprise you, we picked the best one. We should have picked one at random, but we picked the best one. So, using that same technique, we can translate languages. What you're going to do is put in words in one language. Actually, fragments of words work better, but put in words in one language, and it should output words in another language. So you train it, for example, to turn English into French. So there's an encoder part of the network that's taking words in one language. They're going into this recurrent neural network. It's not giving any outputs yet. And after the words in that language have gone into the network, you get some final state of the hidden units. And that final state of the hidden units is vector representation of what this string of words means. The reason we know it's a vector representation of what the string of words means is because we're going to give that vector to another network that's then going to produce this in another language. In fact, now we've got a network that you can give it any language and just tell it what language, any of 12 languages, and just tell it what language you'd like the answer to be in. And the very same network will do all those languages. And that thing that comes at the end of the encoding really is a thought vector. It's like a lingua franca, but it's not a lingua, it's a vector. So I call this a vector franca. The decoder network is given that thought vector, and the first thing it does is say, okay, given that thought, what do I think the first word might be in French? So maybe it's 40% la and 30% la, and so it picks from that and it says, okay, la. So that's the first word. Then you feed that word back into the network and say, the first word was la, what do you think the second word is? And it gives you probabilities. And now you can pick from those probabilities. Each time you do it, you might get a different translation, but it'll give you a good translation of the English sentence. It's amazing that this works, because the network is started with no knowledge whatsoever about language. It just doesn't have any knowledge about grammar or what's going on. It just gets this string of symbols coming in and a string of symbols comes out. And it turns out that's a better way to translate than anything else. In fact, if you go to the web now and try translating Chinese to English or English to Chinese, that's what's going on. Google switched to that and they got a whole lot better. And it's in the middle of switching all the other language pairs. I said that. Now we can get back to my first example. If you take the vision net that recognized objects, and you use the vision net as an encoder, and you take the last layer of the vision net before the output and call that a percept, so that's really the pixels have been turned into a vector representation in terms of objects, and you give that percept to a language decoder instead of the thought that you get from a sentence in another language, until it decodes that percept. That's how the captioning works. So you can't see this very well, but this is a scene of people in an outdoor market. The caption in the database says, people are crouched around in an open market. The system doesn't give as good a caption. It says a group of people are shopping at an outdoor market. But it can clearly see what's going on. And then this example you've seen already. The official caption for that is, a young girl asleep on the sofa cuddling a stuffed bear. That's a better caption than what the system gives. But the point is the system can see what's going on. There's big implications here for document processing. Google would really like to be able to return documents to you based on their meaning, not just based on the words they contain. You can take documents that contain the same words and they can say very different things. Wouldn't it be nice if you could say to Google, give me a document about climate change that purports to be scientific, but actually is a whole bunch of rubbish. And not very soon, but eventually, I think we'll be able to do that. In other words, we'll be able to extract the thoughts from the sentences and look at how the thoughts hang together, because that's just a question of modeling a sequence of thoughts, and we'll be able to see if the thoughts are coherent or if they don't really follow. Now, to do that, we may need much bigger neural nets. One of two things is true. Either we're going to need much, much bigger neural nets, because the brain has about 100,000 times as many connections as the nets we use, or this backpropagation algorithm is much better than the algorithm used in the brain. And I don't actually know which, because the thing that can translate between all these pairs of languages, if you were to look at that on an MRI scan, the size of it would be less than 1 pixel in the MRI scan. Okay? So your brain's got a lot more power than that, but maybe it doesn't have a good enough algorithm. There's an algorithm as good as background. I don't know which way it is. I want to finish with a story, and this is a story about random other applications. So one of the students who did the speech recognition, called George Dahl, saw that there was a competition. He saw rather late, a late stage in competition. There was a competition to predict the activity of a molecule. That is, you're given thousands of things that describe the molecule, like which groups it has and how they're arranged and so on, and whether it's hydrophilic or hydrophobic and all that stuff. And that's the limit of my chemistry knowledge. And you have to predict, will it bind to this target? So some biological target, and if it will bind there, it will be good for treating depression or something. Now, you could synthesize it and see, but that's expensive. Or you could just try and get a computer system to predict, and then you could try millions of molecules. And so Merck put a public competition on the web. And George entered it late, used a neural net, and won. And after he'd won, Merck said, well, there was a $20,000 prize, but part of the condition was, in order to get the prize, he had to tell Merck what QSAR he'd used. And George said, what's QSAR? Now, this is slightly embarrassing because QSAR is actually a field. It's called Quantitative Structure-Activity Relationships. It has a journal, it has an annual conference, it has a lot of people who work in that field. And George had actually done better than anybody could do in QSAR without even knowing the name of the field. He didn't know what any of the inputs represented, he didn't know what the outputs were, he just treated this as a learning problem and gave it to a big neural net, bang. Okay, I'm done, I think. Yes.
So we have time for a few questions, and if anyone has a question, we have microphones here. So just introduce yourself as well. Start here, and Harry, there's one at the front row.
Hi, my name is Ragavan. I'm from a company called Deep Learning. So you mentioned earlier how the vision community was a bit skeptical about the neural networks, and we chatted about a certain scientist's quote. The progress of science is driven by the death of scientists, something along those lines.
Yes, that's right.
Yes.
Progress of science is driven by the death of scientists, but I'm not encouraging you to speed it up.
Yes. So I was wondering do you think something similar can happen with deep learning or neural networks, where we could kind of get into a dogma around it and then not realize other techniques could be useful? Like recently there was the OpenAI paper with evolutionary strategies. It's an extremely simple technique, and it seems to be working very well in reinforcement learning.
Yes, I think that's certainly possible. My plan is not to hang around for too long and let other people take over.
Hi, my name is Seth, and I was wondering, what are the most pressing unsolved problems that face the AI research community? And also how...
Sorry, the face AI what?
That face the AI research community? And also, how close are we to solving intelligence?
Okay. The issue of how close are we to solving intelligence depends a lot on definitions. If you'd asked people a few years ago, they'd have said, well, you can't play Go because these systems don't have intuition, they don't have any sort of perceptual common sense. Now you can play Go, so in that sense we've solved that bit of intelligence. I think we've actually come a long way towards solving intelligence, but we still have a long way to go. There's still major problems, like I don't believe the current kinds of neural networks we're using are going to be what we're using in 10 years' time. I'm an outlier there. Everybody else seems to believe that current neural networks are just fine. We just need a few more ideas and develop them a bit, and they'll be great for applications. I actually prefer disagreeing with everybody else. So I think the current neural networks are going to be replaced by some different kind of neural network, and we don't know what it is yet, and that the field is already in a state where people believe too much in the current technology. Not they believe too much that it works, because it really does work, but they believe it's going to stay like that, and I think it's going to change more than they think.
Hi, my name's Kent. I have a question here about the current way we are organizing the neurons in the neural network. Right now, all those neurons are just organized in layers, and there's no functional or logical grouping of the units. I heard that you are working hard in this area of grouping the neurons in logical ways. Can you have something on this?
Yes, I guess if you're a computer scientist or an engineer, having this great big layer of neurons that are all sort of equivalent to begin with no other structure, just these layers, seems not structured enough. And if you look in the brain's not like that. The brain has things called mini-columns. Neurons talk a lot to nearby neurons and not so much to neurons far away. It has feedback connections. It's pretty different from the simple layered nets. I'm strongly convinced that we need to think about small groups of neurons, and instead of using the nonlinearity we use, which takes a scalar in, it's a linear filter followed by a scalar nonlinearity. I think we need to think of taking a vector in and doing some kind of vector nonlinearity. There's a lot more of those than there are scalar nonlinearities, and people just aren't looking at this, and I think they should be.
Hi, David Tickall. So we talked a minute ago, so you'll know what I'm going to ask you about. I have an interest in self-driving cars, and there's a lot of work being done with deep learning in that area. So I'd be interested in your thoughts on that. Capabilities, limitations, timing issues, all that, implications.
I think it's pretty obvious that I don't know the time scale, but in 5 to 10 years, I think it's pretty obvious to most people there will be a lot of self-driving cars around. It's obvious they're going to save a lot of lives. So some of the jobs they'll make unnecessary, or all those people in hospital emergency rooms dealing with car accidents. Those are jobs we'd rather not have to have. Obviously, it's going to put some drivers out of work too. But in the face of a technology like this, you can't say, let's just not do it. It's going to happen. It's going to happen whether we do it or not. What you want to do is we want to be out in front of it. If you look back at automatic teller machines, I'm sure the same argument went on with automatic teller machines. Automatic teller machines will put bank tellers out of work. But I don't think anybody now would say they shouldn't have been introduced. I don't know, you can probably remember the old days when you wanted to get $20 out of the bank and you had to wait in line for 10 minutes. We don't want that.
Between 10 and 4.
Microphone. Oh, okay, so obviously for the vision systems of these cars, deep learning is going to be very helpful. Not necessarily pure deep learning. I mean, deep learning may be parts of other systems. So Mobileye in Israel doesn't use deep learning, they have a pretty good system. But I think they will switch to using deep learning in addition to whatever they're doing now. Raquel Urtasun at the University of Toronto uses some deep learning and some other vision stuff, and has a very impressive system that will, with an ordinary TV camera, look at a busy intersection and then give you a plan view, which is what you need for navigating, of where all the cars are and where they're going. So this stuff's going to be extremely helpful there, but not necessarily purely by itself. One place I know it's very helpful is for detecting pedestrians. So at Google, they had a system for detecting pedestrians that got it right 99% of the time. And then they introduced a deep learning net, and it got it right 99.9% of the time. And we just need another few nines and we'll be okay.
Hi, I am Yasmin Sodagar from Neuroscience. We are at table A4 at the exhibit. My question is, how do you define consciousness?
I don't really believe in it. I get by fine without it. So, part of the point of neural networks is people don't work by logic, they work by analogies. They do logic when they get to be old and when they're thoroughly trained, but really they work by analogies. So I'm going to answer this question with an analogy. 100 years ago, if you asked a biologist, what's life? Many biologists and philosophers would say, well, things are alive if they have vital force. And once the vital force goes out of them, they're dead. That's not really a very good explanation. It's an attempt to explain something really complicated by assuming there's some kind of essence, and with this essence you got it, without this essence you haven't got it. And that's just how people use the term consciousness. I mean, it's got many different meanings, but the sort of primary meaning is you've got this very complicated thing that's doing these very complicated computations, and if it's like us, it's got consciousness. I don't think that really explains anything. And I think it's not that we won't have consciousness, it's just we'll stop using that term. If a biologist now used the term vital force, you'd just laugh at them, because we have molecular biology. We know what's going on, at least to the level where we don't need to use some vague general essence to explain everything. And I think consciousness is a vague general essence that's meant to explain complicated mental phenomena, but can't.
So we have one more.
Neural networks can be thought of as an approximation function. I'm wondering, and like each data point has a different, like how close it actually matches the distribution. I'm wondering if there's any work on like figuring out the confidence interval or like some measure of how well it works within certain data points without just human intervention.
Yes, there's a huge amount of work on, if you train a neural net and does this well on the training data, can I prove anything about how well it's going to do on test data? Can I prove, for example, that if it reliably lands the plane on all the training examples, it will actually reliably land the plane in new conditions? The answer is you can't prove very tight bounds on much of this stuff. It's a question we're very interested in, of course. But these are very complicated nonlinear systems. And it's very hard to prove stuff, and typically when you can prove stuff, the assumptions you need to make to get the proof are way more stringent than the assumptions that apply to what you're actually using. So one good example is, if you have 60,000 data points and you want to predict something, a statistician will tell you you should use far less than 60,000 parameters. So I recently trained a neural net to identify handwritten digits. There were 60,000 training samples, and I used 250 million parameters. And it worked better than the one that only had 100 million parameters. This is a completely different range from what statisticians are used to. But it is the range that the human brain is in. So you live for 10 to the 9 seconds, and you have about 10 to the 14 parameters. So you have to set 100,000 parameters per second. That's not what statisticians are used to. And we don't know much about this regime. But statisticians are beginning to get very interested, and mathematicians.
So we have time for maybe one more. Over here.
My name is Tariq Habib. First of all, welcome back to Canada from Google. I wanted to know your thoughts on application of deep learning on emotion detection. What's the current status of this in terms of real use cases? Emotion detection.
Okay. First of all, I'm not coming back to Canada from Google. I used to work for Google in both Canada and the States, and now I'm working for Google full-time in Canada, almost full-time in Canada, and then spending some time advising the Vector Institute. So I haven't left Google, despite what you might have read in the Star. I still work at Google.
You brought Google back.
I actually got Google to set up a basic research lab in Canada. So I don't know if you remember, when Brown Mulrooney negotiated to pay much more for our pharmaceuticals, part of the deal was that those companies would put some basic research in Canada. And I don't know how much basic research they put here, but not much. Google is now setting up 2 basic research labs in Canada, one in Toronto because of the Vector Institute, and one in Montreal because of the Mila Institute, which is the sort of sister of the Vector Institute. And that's what we would really like. We'd really like the basic research to be going on here, and the people who do the basic research to pay their taxes in Canada. So, that's progress. Now your question. So neural nets are quite good at emotion detection. I did some work on that a few years ago with a student called Josh Suskind. They're getting better. They're much better than they were a few years ago. And I don't see why they shouldn't end up being better than people, particularly computer scientists, because many computer scientists are on the autistic spectrum, and autistics are very bad at recognizing facial expressions.
So we'll take one last question from over here.
Hi, my name is Daniel, and basically you did mention sort of brain and neuroscience quite a bit, right? But my question is, how much and how often do you work with neuroscientists, biologists, and in light of recent news from, let's say, Musk, for example, are you guys working at all on the brain-machine interfaces, anything like that?
Okay, I'm not working on brain-machine interfaces, but I do talk to neuroscientists a lot. And the whole reason for believing that this stuff might work was the fact that the brain works. Anybody in their right minds would not have said you could take pixels and you could take words and you could get from pixels to words without hand programming lots of stuff in between. The only reason for believing that might be possible is that that's what we do. Nobody programmed us. Evolution puts some stuff in, but not complicated programs. So neuroscience is the inspiration for this, and the way I see it is we're trying to build a bridge. On one end you have empirical scientists who are looking at data and trying to figure out how this thing might compute. At the other end of the bridge you have computer scientists who are looking at computation and trying to figure out how it might be done in a more brain-like way. And so we're trying to build this end of the bridge towards those guys. There's other people in AI trying to build a bridge this way, but that's not going to link up with neuroscience. So it's the inspiration for many of these techniques. And just to give you one example, there's a new direction in neural nets, which is to say, we're not just going to have neural activities and weights on the connections. we're going to have weights on the connections that change at many different timescales. So we'll have weights that change slowly and weights that change much faster. The weights that change fast will hold temporary memory, the weights that change slowly will hold longer-term memory, but we won't have to keep all the temporary memories just as activities. Now that direction is inspired by the fact that real synapses are like that.
Okay, so I'd like to thank Jeff for that incredible lecture and all of you for your engagement. I also want to thank Professor Polanyi for the introduction and for reminding us of the two mountains. And I know you spent a lot of time climbing the first mountain of discovery, and you're now trying to build a tightrope between the two and doing an incredible job of it. And this is what the university and entrepreneurship is all about. And I want to thank RBC, who's helped make this lecture series possible. We are looking forward to another dozen or so of these events, and the topics are going to cover that span, the tightrope between research, innovation, and entrepreneurship. RBC's also made an incredible commitment to supporting the university and our students. We're partnering with them to develop OnRamp, which is going to provide 15,000 square feet of collaborative workspaces for student entrepreneurs. They're supporting Creative Destruction Lab at the Rotman School of Management. We've got fellowships, innovation, entrepreneurship prizes, and this afternoon we're going to have the first annual RBC Prize competition. So it's my pleasure to invite John Stackhouse to the stage from RBC, who's our partner in this, to make a quick presentation and some remarks. And we have some gifts for our guest speaker. John?
Hey, go grab food. I'll keep the seats. No?
Okay, well, thanks, gentlemen. Thank you, Vivek, for those kind remarks.
Well, I mean, if you can get one, get me one.
Behalf of RBC.
Chicken or
First of all,
turkey?
Thank all of you for your
Chicken
passion
or turkey?
in artificial intelligence and machine learning, in discovery and in sharing discovery with the rest of humanity. To thank U of T not only for the great investments you've made in machine learning over the decades, but also for your commitment to entrepreneurship in an academic environment. It's really a model for universities across the country. And especially to thank Dr. Hinton for being such an inspiration, a hero to many of us, and a great, great Canadian who has helped lead us to a special place. This has been a remarkable week in the modern history of Canadian learning. If you could have been there yesterday, many of you were at the launch of the Detector Institute. It was a moment for the country. A lot of politicians were there sort of grabbing the limelight, but it was really a recognition and a celebration of the heroic journey that Dr. Hinton has been on, sometimes alone, sometimes with many of you, but now with much of the country behind us. So let me thank you, Dr. Hinton, for getting us to this place. We did a video interview with Dr. Hinton just before today, and he said something very interesting, that when you, as an academic, you ask governments for money, they usually don't give you as much as you ask for, and it's almost always less than you need. But what we've seen this week is government stepping up and giving actually what we need at this moment in time. And at RBC, we've been proud to be part of a bit of the hustling, but also the commitment to that through the Vector Institute, and with the Prime Minister's announcement yesterday of a pan-Canadian artificial intelligence initiative, of a statement to the world that Canada is in the game. And all of us as Canadians, whether we're scientists, entrepreneurs, investors, or large corporations, or just individuals and citizens, we're in this together. We believe in machine learning, and we believe that Canada has a special responsibility and an opportunity to craft maybe a new kind of machine learning and artificial intelligence that benefits the planet in that Canadian way. And we're looking forward to Dr. Hinton and all of you here at U of T for leading us on that way. Now, I don't want to get in the way of a crowd at lunch. We've got some gifts here for the speaker, but I did want to acknowledge a couple of special things that RBC is doing to help in the AI journey. The first of all is the launch of Next AI, so for entrepreneurs in the room, We're working with Next Canada to help you build great companies in this space that can be the global leaders of tomorrow. And through RBC Research, led by my colleague Polanyi Gaffiotti here, she'll be around afterwards. Come visit our booth, see what we're doing to advance machine learning through RBC. We're building a team of scientists connected to U of T because we think a business can do something special in this space, but we want to learn from you and we want to share with all of you in this wonderful journey. So thank you all for including RBC not only in today, but in these great moments of deep learning in Canada and at U of T. And thank you, Dr. Hinton, again, for a wonderful lecture and again for all you've done for Canada.